Good afternoon, everybody. So my name is Julien. I'm a PhD student, and I am currently working in a French university called Institut Agro. And I am also under contract with the Green Spaces Department of the City of Paris. So, as the previous speakers, that I thank first and I congratulate for their work, which is very complementary to what we are doing here. So I also work with the cooling benefits of street trees, and especially during heat waves and droughts. So the ongoing climate change is coming with an increasing an intensification and a multiplication of extreme climatic events such as heat waves and droughts. And heat waves may be very harmful, especially in cities, which already experience overheating through the urban heat island effect. So the human bodies are exposed to an increasing human thermal stress, which may cause sanitary issues. And street trees may help cooling our cities, or may provide some cooling benefits through their shadows they cast and the water they transpire. But we may wonder how those benefits may vary with the considered tree species, with their respective characteristics, and also with the access to water. Because we know that trees need water to develop, and we also know that water in some regions may be rarefying, especially because of the multiplication of droughts. So in the literature, we can find many studies that already try to assess the climatic benefits of street trees by evaluating different variables which are directly, more or less directly related to those benefits. Some of them try to compare different tree species. Some of them also try to relate some of these variables to the water availability. But there is a general lack of long in-situ continuous monitoring of the climatic benefits of the trees in terms of human thermal stress reduction, comparing different tree species at the same time, and with a consideration of the water availability, or at least with the comparison of different periods with or without rain. So the Trees and Climate Study, which was launched in 2018 by the City of Paris, would like to bring some answers to these questions if possible. So this study was based on the study of 36 trees, mature trees, from 9 different tree species located in 5 different sites in Paris. And but for today, we're only going to focus on one site, which gathered 15 trees from 5 different tree species. So we had 3 trees for each tree species. And they were distributed, as you may see here, on a long northeast-southwest avenue in the northeast of Paris. And this avenue forms an urban canyon. And so today we're going to focus on these trees. And for this experiment, each tree was equipped with a set of meteorological sensors aiming at calculating the universal thermal climate index. So we're talking about air temperature and relative humidity, globe temperature, and wind speed. And those sensors were placed in some branches of the trees in order mainly to avoid the damage that may occur to these sensors. And also, on each site, one reference lamppost was equipped with the sensors in order to gather some reference measurements to be compared with what we have in the tree canopy. Also, each tree was equipped with one sensor on one branch, aiming at measuring the branch diameter variations in real time, which is an interesting variable because it may give information on the water fluxes going on inside the tree, but I will explain it a bit more later. So we could monitor these variables during 4 years, from 2019 to 2022. And today, just to give you, to show you what we're going to look for with this study, we focus on a few weeks period at the beginning of summer 2019. And we chose this period because it was quite warm, with 2 heat waves identified in yellow here by the French Meteorological Institute. And it was also quite dry because it had 27 days without any rainfall, which for Paris is not that common, but is becoming more common with the actual climate change. And so today we're going to try first to look at what we can have as climatic benefits at the beginning of this period. Then we're going to try to assess the evolution of our branch diameter all along this dry period. And finally, we're going to try to compare what's going on at the beginning and at the end of this period. And to do so, we're going to compare 2 sets of 3 days, which are chosen in order to have quite close meteorological condition, or at least as close as possible, as close as we could find. So first, if we focus on our first 3 days, so before the beginning of the dry period, here is what we can get regarding air temperature and UTCI in our tree crowns with the colored lines, and in our lamppost with the black line, where there are different interesting things we can see here. First, there is like a common pattern, a common behavior that seems to be followed by all trees, but we have sometimes some strong differences that are temporary, but that may be linked to the high heterogeneity of our setup, because you may have to know here that our canyon, for instance, doesn't have the same aspect ratio all along the street, because it's very hard to find trees in the same conditions. They may be at different distances from the surrounding buildings. Also, the sensors inside the tree canopies may be at slightly different positions. So this may explain those differences. Then, if we take a look at one single day, for example, this one, we see that there is a variability of the climatic benefits along the day. So here for air temperature, we observe the reduction mainly in the late afternoon. And for UTCI, we can see that it's observed during daytime on a wider period. We can also see that at night we have this greater UTCI inside the tree canopy, which was already reported in the literature and is generally associated to the lower sky view factor below the canopy. And we can also see that there is a variability over the days. For instance, our air temperature reduction isn't constant over the days. And this may be due to the different meteorological conditions, as each day is never exactly the same as the previous one, even if I said that we tried to choose close days with close meteorological conditions. And then if we want to compare our trees, we might want to take one values, but there are plenty of values we could take here to compare our different days, different trees. So for this presentation, we focused on the maximum difference we could observe on each day, and we tried to average it over the 3 days period we are studying here. And what's interesting is that, for instance, regarding air temperature, there is one Ulmus resistor that is at the same time, that is the one that provides the greater air temperature reduction, and another Ulmus resistor provides the lower air temperature reduction of all our trees, which means that here that the variability we may have between our individuals is maybe greater than the variability that may exist between our tree species for this experiment. So now let's take a look at the branch diameter variation. So to explain it a bit more, So this is the kind of signal we might expect for a single tree during 1 year for a tree that is going on well. So we can see easily periods of no growth in winter, which represent the dormancy period, and periods of growth, so from spring to autumn, with the biomass production of the trees. And if we take a look at a few days period, we can see daily variations. So first, we can see a daily shrinkage during the day, which may be associated to the water contained in the tree being spread out through the transpiration process. And at night, we can see a daily increase of the branch diameter, which may be associated first to the water refill, the water being pumped, uptaken in the soil, and then to the biomass production, as we can see that the maximum diameter that is reached each day is increasing. So, knowing this, here is what we could observe during our studied period. Here we picked up 2 trees to make things easier, but we could do it for all our trees. And what we did here is we drew in black the maximum diameter ever recorded, which is a value which can only increase. And we can easily see that we have very contrasted behaviors between our 2 trees. For instance, our Celtis australis is slowing down its growth and even stopping its growth very early in the season. And he never grew again during the studied period. We could also see that this tree is progressively shrinking, so his branch diameter even decreases among time, which may lead us to think that maybe he dried part of its tissues to find water, maybe to keep transpiring. So we could see very contrasted behaviors, as the humus resistant did not show the same behavior. Only its growth was reduced, slowed down at the end of the period. And finally, to compare all our trees and to compare our periods at the beginning and at the end of our dry event, we computed 3-day averages of this shrinkage for each tree and for both periods to see what can to average to look at all our trees at the same time. So this is what we get. So here is a 3-day average of this shrinkage. And first, we can see that some trees have already important shrinkage even at the beginning of the dry event, which may say that they are very sensitive to the lack of water. Whereas other trees, like the platanus or the ulmus, they are not experiencing the same thing. Then we can see that for some trees, there is an increase of the shrinkage during the dry period. So we can take a look at the Celtis one that we just saw previously. And so Celtis seems to have been impacted, whereas some of the Sophora and some of the Tilia, but not all. And the Platanus and Ulmus didn't seem to be really impacted by this dry event, or at least regarding this indicator. And finally, if we add on this graph the air temperature and UTCI reduction, here is what we get. So here we are displaying 3 days average of the maximal, the daily maximal air temperature reduction and UTCI reduction. So we can see slight differences between our trees, between the beginning and the end of the dry period. But what we can see here is that those differences, compared to the standard deviation that is displayed in red here, they are quite low, which means that the differences due to that we observe, they are not that significant when compared to the differences that are due to the meteorological conditions, because this standard deviation is due to the 3-day average that we are making here. So, to conclude, we had on this small analysis very contrasted responses of the trees regarding this dry event, but all trees kept providing interesting cooling benefits and significant cooling benefits, which may lead us to think that this dry event was maybe not dry enough, maybe not long enough to have a real impact on tree transpiration and radiation interception. Unfortunately, we cannot measure in detail those two variables on this setup. We would like, but we can't. And we can see that we can sense that there is a strong variability due to the meteorological conditions. So in the next step of the project, we'd like to take advantage of the whole data set that we have to expand those analyses and to go further in some points, especially to analyze, for instance, the influence of those meteorological conditions. And I didn't mention that we had LiDAR measurements made on our trees that helped us to compute a few morphological variables that we'd like in the end to cross-analyze with the climatic benefits that we are measuring. And I thank you for your attention.
Great work, thank you very much. I really liked seeing those physiological parameters in the dendrometry, which I've done extensively. Any question to finish up this session before I wrap up? There's a question over to the right.
Thank you for the interesting results. So regarding the water, the responses, the different responses on water shortage, do you think it can be because of different root growths under the street? So they're all street trees, and we know that because of the different soil properties, the root growth can be quite different compared to park trees, but also maybe there's difference between different species.
Yeah, this may be part of the explanation, and unfortunately we are completely blind about the root system in this environment, as those trees that were equipped may be 20, 30 years old, and so there was already concrete, there was no pits dug to see the root system. So even we could have some tree, I don't know, close to water pipe that is having like salt water, but we cannot see it here. That's part of it.
There's one more question, the gentleman with the t-shirt.
Thanks for the presentation, Julien. It was very interesting. You used a black globe thermometer to calculate mean radiant temperature for the UCCI. How did you, I mean, there are so many different algorithms to get from global temperature to mean radiant. How did you go about selecting the one that you used?
Well, we used a formula. I couldn't cite it by memory, but that is generally really used in the literature. I think that the main author was Cantor, but this one. Sorry, I didn't cite it.
No. Thank you.
All right. Thank you, Jerry.
Thank you.
Thank you. So within this session, just to wrap up, we learned that Phoenix doesn't have enough shade trees, and 92% of their streets are not walkable. We heard from Prague that trees are not really cooling the air. We heard from London in Canada that a great street surface temperature model is in development. Dominic demonstrated that trees are most effective for cooling at intersections. And from Thierry, we learned that London plane trees are the actually coolest trees in Paris. Thank you, everyone. Enjoy your